So, hey everyone, welcome back to the series. We're 5 videos in now, and I'm really glad you're still here, hanging out in the basement of the stack with me. We've spent a lot of time, honestly maybe too much time, talking about how data moves. We talked about radio waves and BGP gossip and the speed of light. But today I want to talk about something that's actually a bit more existential. I want to talk about persistence. See, as programmers, especially if you're just starting out or you're in that mid-level phase of your career, you live in a dream world. Most of your time is spent in what I call the volatile mind of the computer. When you're writing code in Python or Java or Go, and you create a variable, let's say user ID equals 10, that data feels very real to you. You can see it in your debugger, you can print it to the console, but it's not really there. It's a ghost. It lives in RAM, and RAM is, well, it's a dream that ends the moment the power cord is pulled. If the electricity stops flowing for even a millisecond, every variable, every object, every state in your application just vanishes. It's gone. It's like it never happened.
And that's kind of terrifying, right? I mean, think about it. We build these massive systems, banking apps, medical records, social networks, and the entire thing is fundamentally fragile. If we want to build anything that actually matters in the real world, we have to find a way to take that dream in the RAM and carve it into something permanent. We have to hit the disk. We have to commit the data to the truth. But here's the problem, and this is the first principle we're going to explore today. The disk is a lie, and the disk is slow. I mean, it's really, really slow. It's so slow that almost the entire history of operating system design is just a series of clever lies to hide that fact from you. I want to ground you in the numbers again. I know we looked at them in video 1, but I want you to really feel them this time, especially if you've never had to worry about hardware before. Let's do the human scale mental model. If one CPU cycle, one tick of the clock, is 1 second, okay, 1 second of human time, reading from your L1 cache is like reaching for a pen on your desk. It takes half a second, easy. Reading from main memory, RAM, is like walking to the end of your hallway to get a snack. It takes maybe 2 minutes. You notice the delay, but it's fine. Your life moves on. But reading from an SSD? On this human scale, where the CPU is now, the SSD is 2 days away. You ask for a byte, and you have to wait 48 hours for it to arrive. And if you're still using an old-school spinning hard disk drive, HDD, that's 5 months. You ask for a piece of data, you go through a whole semester of college, you go on summer break, and then, maybe, the disk finally gives you the byte you asked for in January. I want you to really think about that gap. Your CPU is sitting there, capable of doing billions of operations per second, and it asks the disk for a piece of data, and then it just waits. It waits for the equivalent of months in its own timescale. This is the central tension of all system design. We want our data to be persistent, so it survives a crash, but we want our apps to be fast. And those two goals are diametrically opposed by the laws of physics and the current state of our hardware.
So, how do we solve this? How do we build apps that feel fast if the disk is literally months away? To solve this, we've built these incredibly clever abstractions called databases. But for a lot of people, databases are just these magic black boxes. You run npm install pg, or you set up a MongoDB Atlas cluster, and you just assume it works. But if you want to grow into a senior architect role, you have to look under the hood. You have to understand that every database, no matter how fancy the marketing is just a very sophisticated way of managing file I/O. It's just code that is trying to trick the disk into being faster than it actually is. Let's look at the first lie, the pinky promise of the operating system. Imagine you're writing a simple Node.js or Python script. You open a file, you write hello world, and you close it. The write function returns a success code. You think, great, it's saved. No, it's almost certainly not. You see, the operating system, Linux, Windows, whatever you're using, it knows the disk is slow. It knows that if it actually waited for the physical hardware to save those bytes, your computer would feel like it was broken. Your mouse would lag, your Windows would freeze. So the OS lies to you. It takes your data, puts it in a page cache in RAM, and says, yeah, sure, I got it. I'll write it to the disk later. Don't worry about it. Go back to your code.
This is called buffered I/O. It's great for performance, but it's a disaster for persistence. If the power goes out 1 millisecond after that write call returns, your data is gone. It was never on the disk. It was only in the OS's imagination. In the world of databases, we call this the durability problem. To solve this, we have a special system call called fsync. When a database like Postgres calls fsync, it's telling the OS, I don't want you to buffer this. I want you to flush those bytes to the physical hardware, and I am going to sit here and block my entire process until the hardware confirms the physical magnetic platters or the flash cells have actually changed. This is the most expensive call in software engineering. Fsync is the moment of truth. It is where your performance goes to die. If you call fsync after every single write, your database will be incredibly safe, but it will be incredibly slow. You'll be lucky to get 100 writes per second. Think about that. Only 100 users per second could save their data. That wouldn't even run a small Discord server. So how do we fix this? How does a system like Postgres handle thousands of transactions per second while still being durable? They use a beautiful pattern called the write-ahead log, WAL. I love the WAL because it's so simple and so effective. Instead of trying to update a complex data structure like a giant table with millions of rows and 5 different indexes on every single write, the database does something very junior but very fast. It just appends the change to a long sequential file called the log. User 5 changed their name to Andre. Boom, append. User 10 deleted their account. Boom, append. Appending to the end of a file is the fastest thing a disk can do. It's sequential. It doesn't have to move the head of the disk or search for space. It just stays at the end and keeps pouring bytes. The truth lives in the log. If the database crashes, it doesn't care if the main table is corrupted or out of date. It just replays the log from the last known good state. It's like if you're a chef in a busy restaurant. You don't update your final inventory book every time you use a single egg. You'd be spending all your time walking to the office to write in the book. Instead, you just scribble used 1 egg on a notepad on your counter. That notepad is your write-ahead log. At the end of the night, when the kitchen is quiet, you use the notepad to update the big book. The notepad is fast, the big book is slow. Now I want to take a side quest into the hardware itself. We've been talking about the disk as one thing, but SSDs and HDDs are fundamentally different physical objects. And if you're a junior to mid-dev, you might think SSDs are just really fast RAM. They're not. They're much weirder than that. In an old HDD, there is a physical arm and a spinning platter. It literally has to move. It's a mechanical robot. If you do a random read, that arm has to fly across the disk. This takes time. That's why we love sequential access. But even with SSDs, which have no moving parts, we still have problems. SSDs are made of flash cells, NAND. And here's a weird fact about the physics of flash memory. You can't just overwrite a cell in an SSD. If a cell has a 1 and you want it to be a 0, you can't just flip it like you do in RAM. You have to erase it first. But wait, it gets worse. You can read and write in small pages, usually 4 kilobytes or 8 kilobytes, but you can only erase in large blocks, maybe 2 megabytes. Think about how annoying that is. If you want to change 1 single byte in the middle of a 2 megabyte block, you can't just change it. You have to read the entire 2 megabyte block into RAM, change the byte in RAM, erase the 2 megabyte block on the disk, this takes a long time, and write the modified 2 megabytes back to the disk.
This is called write amplification. You wanted to write 1 byte, but the physical disk had to move 2 million bytes. This is why SSDs get slower as they get full. They run out of clean blocks to write to, and they have to start doing this read, modify, erase, write dance.
To hide this nightmare from you, every SSD has a flash translation layer, FTL. It's basically a tiny computer with its own CPU and its own tiny bit of RAM living inside your disk. It is constantly moving your data around in the background to wear level the cells. It's trying to make sure you don't use the same cell over and over again until it dies. And yes, SSD cells do die. They have a limited number of program erase cycles. If you write to the same spot 1,000,000 times, that cell will physically break and stop holding a charge. The FTL is like a master architect, constantly shifting your data to fresh cells so the disk lasts for years instead of weeks. Why do I tell you this? Because it means even your SSD is lying to you. When you write to sector 10, the FTL might actually put that data on physical cell 5000 and just remember the mapping. This is why sequential writes are still better on SSDs. If you write sequentially, the FTL can just pour the data into clean blocks. If you write randomly, you trigger garbage collection inside the SSD, and your performance drops off a cliff. Now, let's go back to the software side. We have our write-ahead log, which is fast, but as we discussed, searching a log is slow, so we need an index. And the king of indexes is the B tree. Now, don't let the word tree trigger any bad memories from data structures class. I want to talk about a paper from 1979 called The Ubiquitous B Tree. In computer science terms, 1979 is the Stone Age, but almost every database you use today, Postgres, SQL Server, even the file system on your laptop, it's still built on this paper. Why? Because the B tree is perfectly tuned to the physics of the page. See, as we talked about, the disk doesn't read 1 byte at a time. It reads in pages, 4 kilobytes or 8 kilobytes. It's like a delivery truck. It doesn't matter if the truck is carrying 1 envelope or 50 boxes, it still has to drive across town. So a B tree is designed to be fat. It has a high fan-out. Instead of a node having 2 children, like a binary tree, a B tree might have 500 children. Let's do the math. This is kind of fascinating. If each node has 500 children, layer 1, the root, 1 node, can point to 500 pages. Layer 2, 500 nodes, can point to 250,000 pages. Layer 3, 250,000 nodes, can point to 125 million pages. Layer 4, 125 million nodes, can point to 62.5 billion items. Think about that. With only 4 layers, you can index 62 billion rows of data. This means that to find any piece of data in a massive database, your CPU only has to make 4 trips to the disk. When you run an SQL query, you are performing a guided descent through this shallow tree. Trip 1. Load the root page from disk. Trip 2. The CPU looks at the keys and says, okay, the ID we want is between 10K and 20K, so go to page 45. Load page 45. Trip 3, look at the next set of keys. Go to page 1002. Load page 1002. Trip 4, grab the actual row. In about 30 to 40 milliseconds, roughly the time it takes to blink, you've found one specific needle in a billion-row haystack. That is the magic of the B tree. It is shallow, it is fat, and it understands that the disk is slow, so it makes every trip count. But the B tree has a major weakness. It requires random writes. If you want to update a row, the B tree has to find that specific page, read it into memory, change it, and write it back. This is called read, modify, write. And if you're getting thousands of updates per second across the whole tree, you're forcing the disk to bounce around like crazy. It's like trying to deliver 1,000 packages to 1,000 different houses in 1,000 different cities. No matter how fast your truck is, the driving time will kill you.
And that's where the contender comes in, the LSM tree, log structured merge tree. This is what powers modern NoSQL databases like Cassandra and RocksDB, and even the Wired Tiger engine inside MongoDB. The LSM tree engineers took a very different, very first principles approach. They said, what if we never, ever do a random write? What if we only do sequential writes? This sounds impossible, right? How do you keep a database organized if you only ever append to the end? Here's how it works. When you write data to an LSM tree database, it doesn't even look at the disk. It writes the data to a sorted list in RAM called a mem table. Writing to RAM is, as we know, lightning fast. But RAM is volatile, so at the same time, we scribble the write to a write-ahead log on the disk. The wall is sequential, so it's also fast. Once that mem table in RAM gets full, say it hits 64 megabytes, the database does something clever. It freezes that mem table and flushes it to the disk as a single sorted file called an SS table, sorted string table. Now, here is the secret. SS tables are immutable. We never change them. If a user changes their name from Tom to Tim, we don't go back and find the old file and update it. We just write the new name in a new SS table. Now, you might be thinking, wait, Tim, if I have 1,000 SST files on my disk and I want to find a user's name, do I have to search all 1,000 files? That sounds slower than a B tree. And you're right, it would be. So we use two more tricks to make reading fast. First, we use a Bloom filter. This is a beautiful piece of probabilistic math. It's a tiny bit of data in RAM that can tell you, I am 100% sure that user 123 is not in this SST file. If the Bloom filter says no, the database doesn't even bother opening the file. This saves us from thousands of wasted disk trips. Second, we do compaction. In the background, while your app is running, the database has a janitor process. It takes small SST files, merges them together into bigger files, kind of like merge sort, and throws away the old, deleted versions of the data. This leads us to something called the conjecture. Read, update, and memory. It's a law of the universe that says you can only optimize for two of these at once. B trees optimize for reads, very shallow trees. LSM trees optimize for updates, sequential appends. As a junior to mid-engineer, you need to know which one your database uses. If you're building a logging system that gets 10K writes a second, but you rarely read the data, and you use a B tree database, you're going to have a bad time. You're fighting the physics of the disk. If you're building a banking app where you need to read balances instantly but writes are rare, use a B tree. I want to talk about something that most junior devs never think about until it's too late: bit rot. We like to think that once a bit is on the disk, it stays there forever, but the universe is a messy place. We have cosmic rays, literally high-energy particles from space that can fly through your data center, hit a single transistor on your disk, and flip a 1 to a 0. We have electrical decay, where the charge in a flash cell slowly leaks out over years. This is silent data corruption. Your database reads the file, it looks like a valid file, but the user's name is now Andre instead of Andrew. Senior engineers don't trust the hardware, they use checksums. Every time a modern database or file system, like ZFS, writes a page of data, it calculates a mathematical summary, a hash of that data, and stores it next to it. When it reads the data back, it recalculates the hash. If the hashes don't match, it knows the disk lied. This is the first principle of reliability. Hardware is a suggestion, software is the enforcement. If you are building a system where data integrity matters, which is basically every system, you should be asking, how does my storage layer detect bit rot?
If you're just saving raw JSON files to a basic disk, you are living on borrowed time.
Now, let's scale up one last time. What happens when one disk isn't enough? If you're Google or OpenAI or you're building a big fintech app, one disk is a joke. Even the best SSD in the world has a mean time between failures. If you have 10,000 disks in a data center, the math says that one of them is failing right now as you're watching this video. It's just a matter of statistics. So we have to move from physical persistence to distributed persistence. The Bible for this is the 2003 Google File System, or GFS paper. I highly recommend reading it. It's surprisingly easy to understand. The GFS engineers made a profound observation. Component failures are the norm, not the exception. Most engineers build systems and hope they don't fail. Google built a system that expects to die every single day. The solution is replication. In GFS, when you save a file, it's broken into chunks, 64 megabytes each, and the system doesn't just save that chunk once, it saves it 3 times on 3 different machines in 3 different racks. Why 3? Because of the power of 3. If one disk dies, we don't care, we have 2 more. If a whole rack of servers loses power because a fuse blew, we still have 1 more copy in a different part of the building. While we're fixing the broken ones, the 3rd copy keeps the system alive. But this creates a consistency nightmare. This is where junior engineers often get stuck. Imagine you have 3 copies of a user's balance. Copy 1 says $100, copy 2 says $100, copy 3 says $50 because the network was slow and the update didn't arrive yet. If the user checks their balance and they hit copy 3, they're going to be very angry. Who has the truth? This is why persistence at scale isn't just a disk problem anymore. It's a coordination problem. We use consensus algorithms like Raft or Paxos, which we'll spend a whole video on later, to make sure the 3 machines agree on the value before we tell the user success. When you use a service like Amazon S3, you aren't just saving a file, you are triggering a massive distributed coordination game. S3 is effectively GFS on steroids. It's writing your data to multiple physical buildings simultaneously, so that even if a literal meteor hits one data center, your data survives. But remember video 3, this replication has a latency tax. Writing to 3 places is slower than writing to 1. This is the ultimate trade-off. Do you want it fast, or do you want it forever?
So let's wrap this up. What is the takeaway for you today? Persistence is not a binary. It's not saved or not saved. Persistence is a spectrum of risk. Think about this for a second. If you write to RAM, your risk is high. The power goes out, you lose it, but it's lightning fast. If you write to a local SSD with a standard write call, your risk is medium. If the app crashes, it's fine. If the OS crashes, you might lose it. If you write with fsync, your risk is low. It's on the metal, but it's slow. If you replicate to 3 disks in 3 different cities, your risk is near 0, but it's very expensive and has high latency. As an engineer, your job isn't to make everything perfectly persistent. Your job is to look at your data and ask, what is the cost of losing this byte? Is it a like on a post? Maybe an LSM tree with eventual consistency is fine. It's okay if the like takes 2 seconds to show up for everyone. Is it a log message for debugging? Maybe just an OS buffer is fine. If you lose a few logs during a crash, it's not the end of the world. Is it a $10,000 bank transfer? You call fsync, you wait for the B-tree update, and you wait for 3 replicas to say ACK before you show a green check mark to the user. Don't treat your database as a black box. It's just a tool. It's a clever set of tricks trying to manage the fact that your CPU is now and your disk is 5 months from now. Respect the physics, understand the lies the OS tells you, and always know where your truth actually lives. In the next video, we're going to look at the taxonomy of storage. We've talked about how we store bytes, but now we need to talk about what we store. SQL, NoSQL, graph, key value, how do you choose the right model for your truth? I'll see you in video 6.